All right, so we're going to introduce ourselves today to transformers, which are another common circuit element that is often used, particularly in power systems. So the basic concept of a transformer is that I take a set of windings, basically a copper wire, and wrap it around sort of what we call a high mu material. So something that's really good at passing a magnetic field. And we refer to the two sides typically as what we call the primary and the secondary. All right, and there's a different number of turns on each side. So this guy here we'll say has N1 turns, and this guy over here we'll say has N2 turns. Okay? All right. Now, the way that this works is we apply a current into the primary side. Usually this is the way it works. We apply a current to the primary, and then eventually a current appears in the secondary. All right, now the basic concept behind a transformer is that if I were to have a current flowing through this primary, so say it's flowing in the direction that is shown here with this arrow, we know from the right-hand rule that there's going to be fields flowing around this thing, right? So if a current is flowing in the direction that is shown, if you sit at home and do your right-hand rule, that effectively means that I'm going to get fields going around the wire like that. Okay? Now, when the wire gets to the transformer here, to this piece of iron, what's going to happen is that instead of trying to flow in the circle around the wire like that, they're going to basically be trapped to flow through the middle of the iron in the direction of this sort of green dotted arrow. The basic concept of a transformer is that if you take windings and you wrap them around a material that has high mu, like iron, what's going to happen is that high mu material is going to direct the magnetic flux basically into this device, and it's basically going to flow it into the other coil. So you can sort of think of this sort of high mu material, this iron, as sort of a pipe that directs the magnetic field from this coil over to the other coil. And ideally, all of the flux that's created will go up through this coil and end up inside the other one. Now, that's never happens exactly, but in most transformers, it goes pretty close to that. So it works relatively well. Now, in general, we talk about the magnetic flux. And you may remember from physics that flux, phi, is equal to the magnetic field times the area. So A is the cross-sectional area of this guy. All right, we're not going to worry about that too much. I'm just going to say that flux is the total amount of magnetic field that is passing through this core of the transformer, which is what we refer to it as. All right, so the goal of this thing basically is to say, I'm going to wrap a bunch of turns around this core, and what's going to happen is that set of turns is going to take its magnetic field and direct it into this other coil. Now, the primary reason for doing this is what we call Faraday's law. Faraday's law basically said that if I had a changing magnetic field passing through a coil, so if I have a coil like so, and I have a d flux by dt passing through that coil, then there will be a current that is induced in that wire. And that's the basic principle that sort of AC power generation is based upon. So in this case, what we're saying is if I put an AC current into the primary right here, I'm going to get an AC current induced in the secondary. So it's sort of like I have a sort of a transmitter over here on the primary and a receiver over on the secondary that generates a new voltage. So this is a way of creating what we call isolation. All right, so one reason we use transformers is to isolate voltages. In other words, I can basically have one circuit over here causing something to happen somewhere else, just like a radio station sort of concept, right, where I have a sender and a receiver, and they never touch each other. So it's often useful for isolation. The more common thing that people think about is scaling voltage or current levels. So for instance, if I'm looking at a power system, right, I might have a power plant over here. This guy might be at, roughly about 20 kV output. What we typically do is we step up the voltage out of the power plant to a much higher level when you're looking at these transmission towers that you see. This guy might be at 250 kV, for instance. All right, we step the voltages up, and then by the time it gets to your house, I'm down here at 120 volts again. All right, now 120 volts might be what I want, but it's a really bad idea to transmit voltages that are that low, all right, for reasons that we're going to see here in a little bit. Okay, so we typically want to scale voltage levels up and down and correspondingly scale current levels up and down. All right, so the ideal transformer is what we're going to focus on, and the symbol for the ideal transformer is what is shown right here on the left. All right, so we said we had N1 turns over here, we had N2 turns over here, and the way I've defined this is I say, well, on the primary side, I'm going to call the voltage V1 and the current I1, and the voltage V2 and the current I2, okay? And the way we typically do this is, the thing to remember, these are not inductors, okay? These are not inductors. What we are showing here is an ideal transformer, which is shown as these sort of two inductor coils facing each other with the bars in between them. And you always have these dots, okay? We're going to talk about the dot notation here in a second. We're only going to deal with what we consider to be ideal transformers. A non-ideal transformer would be one where some of this flux that's created by coil 1 doesn't reach coil 2. A well-designed transformer, that is typically a really, really small amount of flux that doesn't make it. So it's fair to treat this as an ideal transformer. Okay, if the transformer is ideal, then we can begin our analysis like so. The critical thing is that let's look at coil 1. Coil 1, let's say it has a current flowing through it. That will create a flux that passes through both coils. The critical thing here is if I look at this picture, right, the total flux that's created by both coils is the same going through each one. In other words, there's just a magnetic flux going around this core, passing through both coils. So it's fair to say that the flux going through coil 1 and the flux going through coil 2 is exactly the same. Okay? Now, one of the things that we said is that if I have a coil, all right, so I'm going to draw my coil like this, and if I have a changing flux passing through that coil, all right? In fact, I'll do it carefully like this. Let's say I have one coil for a second. If I have a changing flux passing through that coil, I'm going to have a current flowing through it. Or if, let's say I draw that coil as kind of open circuited, like that. There will be a voltage induced at those terminals of that coil. If it's a changing flux, in other words, if there is a d phi by dt, there is a voltage that's induced. That's Faraday's law. If I have n of these, okay, then the voltage induced here will be n1 times d phi by dt. Okay? In other words, if there's a whole bunch of coils stacked up on top of each other, the total voltage induced is basically the sum of the voltage in each one. So if there's n1 coils, I'd have n1 times the voltage induced in any one of them. Okay? So what that tells us here is that V1 is like this and V2 is like this. The only difference between those two relationships is that there's a different number of turns on the two sides. Okay? So if you solve each one of these, you get basically what I have down here, right? So d phi by dt equals V1 over N1. d phi by dt also equals V2 over N2. Okay? So I get my first sort of key relationship when it comes to transformers. The way of relating primary and secondary voltage, which is that in general, V1 over N1 equals V2 over N2. Now here's the key thing here. This relationship that I wrote right here assumes that the positive terminal of both voltages is at the same place. So we got to explain this dot. In other words, all right, so we drew these dots. So in this particular picture, I have one of them at the dot and the other plus terminal at the dot. So in that case, I have V1 over N1 equals V2 over N2. But if I have this scenario, let's say I have this, and I do a dot here and a dot here, and I write V1, V2 like this, this situation would be V1 over N1 equals negative V2 over N2. All right? What the dot really tells us is something about the way in which the coils are wound around the core. All right, that doesn't really matter a whole lot to you if you're not really winding a transformer, but if you're actually winding one, it matters quite a bit, okay? All right, so this is an important thing to remember. The key thing for you is to remember this basic relationship right here, and then to figure out based on the dots how I use the minus sign or not, okay? Now the second relationship that I always think about is the power relationship. Because power is always conserved, all right, it should be the case that the power into the transformer and the power out of the transformer equals the same thing, or the net power into this device equals 0. So since power is always conserved, if I have the current drawn flowing into the plus terminal on both sides, it better be the case that P1 plus P2 equals 0, right? Where P1 is V1 I1 and P2 equals V2 I2, right? So that's just using our passive sign convention, right? We call power positive when a current flows into a plus terminal, right? And so on the secondary side, it's doing the same thing. Current's flowing into the plus terminal. So that tells us that V1 I1 equals negative V2 I2, right? So essentially what it's saying is the power that flows into the primary flows out of the secondary, all right? Is essentially what that's saying. Now, from that result, we can basically derive the current relationship. So my thinking is that there's no need to really memorize much in terms of formulas. I can look at the voltage formula, which is relatively easy to remember, V1 over N1 equals V2 over N2, and determine whether or not it needs a minus sign on the basis of the dots, okay? I can then write my power relationship and use my power relationship to get the current relationship. All right, so for this case, we knew that the voltage relationship was positive. I can look at this guy and say power equals V1 I1, and on the power 2 side I have V2 I2, and the thing that I need to remember about this is if I rewrite this relationship, I see that V2 equals N2 over N1 times V1, and I plug that in right here, right? So I say that P2 equals V2 I2, or it equals N2 over N1 times V1 times I2, okay? So with that, I go back to this relationship, right? So I plug in P1 equals V1 I1, and I plug in P2 equals N2 over N1 times V1 times I2. The V1s cancel, and I get that I1 equals negative N2 over N1 times I2. So I get my sort of basic relationship, and in this case, I see that I have a minus sign here. That's not, we'll deal with that here in a second, okay? A couple of things to remember about this, all right? And one important check that I always put in here. If you rearrange my equations, all right, no matter what signs that I have, if I have V1 equal to N1 over N2 times the magnitude of V2, and the magnitude of I1 equals N2 over N1 times the magnitude of I2, what I will always see from this is the side with more turns always has more voltage, and the side with fewer turns always has more current, and they're in the exact same proportion. All right, so if I had this example here, so N1 equals 4 and N2 equals 4, so that tells me that the magnitude of V1 equals 4 times the magnitude of V2, right? So the magnitude of the voltage on the primary side is 4 times bigger than the magnitude of the voltage on the secondary. The magnitude of the current on the primary side will be 4 times smaller than the magnitude of the current on the secondary. In other words, I1 equals magnitude I2 divided by 4. That kind of makes sense, right? If power is conserved, what we said here was the power flowing in to this side is equal to the power flowing out of this side. It better be the case that the voltage is bigger on one side and the current is smaller on that same side. Okay? So if I looked at the secondary side, you'd see that the voltage is smaller and the current is bigger. Okay? So, and the relationship's always going to be like that. If the voltage is 4 times bigger, the current's going to be 4 times smaller. All right, that's one quick check that you can always do. All right, so let's look at an example. Let's say I wanted to figure out V1 and V2 and I1 and I2 in this circuit. So if I wanted to do that, our basic process sort of unfolds in 4 steps. All right. First thing I'm going to do is I'm going to write the voltage relationship. Then I'm going to write the power relationship. Then I'm going to use the 2 of those to get the current relationship. And then I'm going to use my basic circuit analysis tools to take those results from the first 3 steps to be able to solve for whatever it is I want. All right, so let's go through that process. All right, so let's look at our ideal transformer in this case. All right, so what I see always is I have V1 over the number of turns equals V2 over the number of turns in the secondary. So V1 over 4 equals V2 over 1. All right, since both sides have their plus terminal at the dot, there's no need for a minus sign. Okay, so that's relatively straightforward. Now it's funny, right, because I've got this sort of flipping going on, right? The dot's here and the dot's here. But in this particular case, the plus sign is at the dot in both cases, right? So there's no big deal. Now, based on the way I1 and I2 are set up, in this case I've got I1 going into a plus terminal. So the power there is V1 I1, okay? That's just using the passive sign convention. Now on the secondary side, it looks like I2 has been defined to be flowing around like this and then into the plus terminal, right? So power 2 is V2 I2, again, just using the passive sign convention, okay? So that tells us that power 1 plus power 2 equals V1 I1 plus V2 I2. So if I combine those, right, I know that V1 over 4 equals V2. We found that before. So into our power relationship, we have V1 I1 plus V2 I2, right, where V2 is V1 over 4. So that gives us this relationship here that I1 is the negative I2 over 4. So in other words, if I check this, the voltage is 4 times bigger on the primary, and the current is 4 times bigger on the secondary. So that should all make sense, right? On the side with the higher voltage has a lower current, and the side with the lower current has a higher voltage. So now, how do I solve for the rest of this now that I have this set of results? Okay, so the simplest thing for me to do probably is to write out a KVL relationship. So let's do that. Let's say I'm going to write out my signs here for each of my devices. So I'm going to say that I've got voltage polarities that look like that. And then I'm going to do KVL for the primary. All right, so on the primary side, I'm going to start in this corner down here, and then I'm going to go around in a clockwise direction. So 0 equals negative 100, right, because I'm going from minus to plus. Plus it equals 32 plus J16 times I1, right, because I went from a plus to minus. And then I go through V1. So I just write that as V1. And then I go from plus to minus on my capacitor. So I have plus I1 times negative J24, because my impedance there is negative. So then I have my KVL for the secondary. So for the secondary, again, I'm going to do the same thing. I'm going to start in this corner right here and go in a clockwise direction. So 0 equals, so I go plus to minus on V2, so I write that as plus. Then I have I1 times 3. Then I have I1 times J2, so I'll write that as J2 not I1, the current on the secondary side is I2, right? Okay, current on the secondary side here is I2, right? And then I go into what I'm going to call VS right here. I don't want to write this guy as 20 with an angle of negative 20 degrees. All right. So just to follow that again, so I'm going to go counterclockwise from the bottom corner here, the bottom left corner. Sorry, clockwise from the bottom left corner. So I go V2 from plus to minus, and then from plus to minus I go 3 times I2, and then from plus to minus I go J2 times I2, and then from plus to minus I go VS. Okay, so there's my relationship. Now what I have essentially here is 4 unknowns and 2 equations, but I can relate 2 of them together. Okay, so let's rearrange this here. I can say that V2 equals negative 3I2 plus J2I2 plus Vs, right? So I just rearrange that by bringing the V2 over to the other side. Now what I can do is I can say, well, I know that I2 has to be equal to negative 4I1. So I will use that here in this relationship and say I have negative 3 times 4 times minus I1. So this becomes negative 12I1 plus J times 2 times negative 4. So this should be minus 8I1 plus Vs. So right, what I did was I just dropped this into this result right here, right? Now, I'm going to bring the V2 into that, right? So I'm going to say I have 12I1 plus J8I1 minus Vs. And I can use my other relationship now, right? I know that I just solved for V2. So in my other equation up here, I have a V1. So I can say that V1 has to be equal to 4 times this result right here, okay? So with that, I can then plug into this equation. So I'm going to go to another slide here. So my first equation was 100 equals J16 plus 32 I1 plus V1 plus or minus J24 I1. Just make sure it's J24. Yep. Okay. So what I do now is I plug in J16 plus 32 times I1 plus V1 is 4 times the relationship we had previously for V2, which is 12I1 plus J8I1 minus Vs, okay, minus J24I1. Now, Vs was 20 with an angle of negative 20 degrees, okay? So all we have to do at this point is, you see I have one equation with one unknown. That unknown here is I1. So I can rearrange that guy and solve for I1. So to do that, what I did was I went to MATLAB here, okay? So let's look at what I did. I basically set this guy up. So I defined what I called the left side of the equation, right? Because what I would have to do here is I rewrite this guy as 100 plus 4Vs equals J16 plus 32 plus 48 plus J32 minus J24, all of that times I1. So I grouped each term, right? So here's J16 plus 32. Here's the 48. Here's 8 times 4 is 32. And then minus 24J is right there. So what I did, the way that I set that up here, is I said the left side of the equation is 100 plus 4 times my Vs. Now notice how I wrote Vs. 20 times exponential minus J20 times pi over 180. Because this is in degrees, exponential by default is in radians. So I did a radian, or a degree to radian conversion. And then I said the right side of the equation was this J16 plus 32 minus 24J plus 4 times 12 is 48, right? Plus 32J. And then I just said I1 is the left side divided by the right side, okay? So that gives me my I1. So I solve my I1 from there. Then if I want to figure out, let's say, everything else, the other thing I have to do is, if I go back to this original relationship, I can say, well, V1 has to be equal to 100 minus J16 plus 32 times whatever I1 is. Remember, if we solve for I1, we know what it is. Plus J24 I1. And I can now solve for V1. Then I basically say V2 is equal to simply V1 over 4, and I2 is equal to simply negative 4 times I1, like so, okay? Because those were our key relationships. So in MATLAB, what did I do? All right, so in MATLAB, what I did here was I said V1 is equal to 100, and then I plugged in, I1 into these relationships here. And then I had my V2 is V1 over 4, and my I2 equals negative 4 I1, and then I can get my results from there. Okay, so one thing we'll check on here real quick is I'll run this, and we'll look at our results. So let's look at a couple of things here. So abs of I1, the magnitude of I1, and the magnitude of I2. All right? So if you look at I1, it's 2.1228. The magnitude of I2 is about 4 times bigger than that, right? Exactly like what we would say, right? And so the abs of the magnitude of V1 is 64. The magnitude of V2 is 16. So again, 1/4. So the side with more windings has a higher voltage. The side with fewer windings has a higher current. Exactly like what we would have expected.